In this video, we're going to go over the following sections. First of all, we're going to create AWS VPC using Terraform. Then we will create AWS Fargate. If you're planning to use only Fargate without EKS node pools, you would need to update CoreDNS deployment. Then we will deploy a simple app to the cluster. We would need to deploy metric server to enable horizontal pod autoscaler to scale up and down pods based on the CPU and memory usage. Sometimes AWS Fargate will patch your pods with security updates, which will trigger pods to be killed and rescheduled on other Fargate nodes. To improve stability, we will create a pod disruption budget for our application. Then we will create IAM OpenID Connect provider to be able to use IAM roles in Kubernetes. We will use it to deploy AWS Loadbalancer controller with Helm and Terraform. To validate deployment, we first create a simple Ingress, and then I'll show you how to secure Ingress with TLS certificate. AWS Loadbalancer controller also can manage service of type load balancer and create network load balancers for them. And finally, if you want to run a stateful application in AWS Fargate, the only option available right now is to integrate cluster with Amazon EFS. EBS volumes at this point are not supported. You can find the timestamps in the video description. All the commands and code are available on my website and GitHub repository. First of all, we need to declare AWS Terraform provider. You may want to update AWS region, cluster name, and possibly EKS version. We're also going to be using a new version of the AWS provider, so let's set constraint here as well. I also include Terraform log file, so if you encounter any issues, try to copy that file and rerun the Terraform. Next, we need to create AWS VPC itself. Here, it's very important to enable DNS support and hostnames, especially if you're planning to use EFS file system in your cluster. Otherwise, CSI driver will fail to resolve EFS endpoint. Currently, AWS Fargate does not support EBS volumes, so EFS is the only option for you if you want to run stateful workloads in your Kubernetes cluster. Then the Internet Gateway. It's used to provide internet access directly from public subnets and indirectly from private subnets by using NAT gateway. Now we need to create 4 subnets, 2 private subnets and 2 public subnets. If you're using a different region, you need to update availability zones. Also, it's very important to tag your subnets with following labels. Internal ALB tag used by EKS to select subnets to create private load balancers, and ALB tag for public load balancers. Also, you need to have a cluster tag with owned or shared value. For the NAT gateway, I prefer to allocate elastic IP address with Terraform as well. We need to explicitly depend on the internet gateway here and place this NAT to one of the public subnets with default route to the internet gateway. The last components that we need to create before we can start provisioning EKS are route tables. The first is a private route table with the default route to the NAT gateway. The second is a public route table with default route to the internet gateway. Finally, we need to associate previously created subnets with these route tables. 2 private subnets and 2 public subnets. Now, you can declare the rest of the components including EKS, but I will do it step by step. Let's go to the terminal and run Terraform init first. Then Terraform apply to create VPC and subnets. The next step is to create EKS control plane without any additional nodes. This control plane can be used to attach self-managed and AWS managed nodes, as well as you can create AWS Fargate profiles. First of all, let's create IAM role for EKS. It will use it to make API calls to AWS services, for example, to create managed node pools. Then we need to attach Amazon EKS cluster policy to this role. And of course, the EKS control plane itself. You would need to use our role to create a cluster. Also, if you have a Bastion host or VPN configured that allows you to access private IP addresses within the VPC, I would highly recommend enabling a private endpoint. I have a video on how to deploy OpenVPN to AWS if you're interested, including how to resolve private Route 53 hosted zones. If you still decide to use a public endpoint, you can restrict access using CEDAR blocks. Also, specify 2 private and 2 public subnets. AWS Fargate can only use private subnets with NAT gateway to deploy your pods. Public subnets can be used for load balancers to expose your application to the internet. After you provision EKS with Terraform, you would need to update your Kubernetes context to access the cluster with the following command. Just update region and cluster name to match yours. EKS was built to be used as a regular Kubernetes cluster. It expects a default node pool to run system components such as CoreDNS. If you run kubectl get pods, you will see that CoreDNS pods are stuck in pending state. Before we can proceed, we need to resolve this issue. You can verify that you don't have any nodes by using this command. To run CoreDNS or any other application in AWS Fargate, first, you need to create Fargate profile. It is a setting that allows EKS automatically create nodes for your application based on Kubernetes namespace and optionally pod labels. We need to create a single IAM role that can be shared between all the Fargate profiles. Similar to EKS, Fargate needs permissions to spin up the nodes and connect them to the EKS control plane. Then we need to attach AWS managed IAM policy. For AWS Fargate profile, we need to specify EKS cluster. Then the name. I usually match it with Kubernetes namespace and IAM role. When you select subnets for your profile, make sure that you have appropriate tags with cluster name. Finally, you must specify the Kubernetes namespace that you want AWS Fargate to manage. Optionally, you can filter by pods labels. Let's go back to the terminal and run Terraform apply. It should take a minute or two. Now, if you get pods again, you would expect that CoreDNS should be scheduled already. But most likely, if the EKS team won't fix it in later releases, those CoreDNS pods will continue to be in pending state. You can try to describe the pod to get some kind of error from the Kubernetes controller. You should get something like no nodes available. If you scroll up, you will see a reason. Those pods come with compute type EC2 annotation that prevents them from being scheduled on Fargate nodes. The fix is simple, just remove the annotation from the deployment template. First, I'll show you how to fix this manually and then a Terraform code. Let's split the terminal and in the first window run kubectl get events. It's very helpful when you need to debug Kubernetes issues. In the second window, just run get pods. Then let's use kubectl patch command to remove this annotation from CoreDNS deployment. When you apply it, it will immediately recreate CoreDNS deployment without those annotations. In a few seconds, AWS Fargate should spin up a couple of nodes. It may take up to 5 minutes. If you rerun kubectl get nodes, you should see 2 Fargate instances. AWS Fargate creates a dedicated node for each pod with similar resource quotas. Now you can patch CoreDNS deployment from the Terraform code. But at this time it will look a little bit ugly. There is a Terraform Kubernetes annotation resource, but it only updates high-level annotations, for example on the deployment object itself. But we need to update pod-level annotations. To patch, let's use null resource. It's just a similar kubectl patch command. It works just fine, you just need to make sure that you have all the binaries in place, such as kubectl, AWS Authenticator, etc. Since I already fixed this manually, I will comment this section out. The next step is to deploy application to AWS Fargate. You already know how to create a profile. Let's create another one for staging namespace this time. The only difference here is a profile name and a selector. With this profile, you can only deploy applications to the staging namespace. Let's quickly apply the Terraform. Now let's create another folder for Kubernetes files. The first file is a simple deployment.yaml. In the future, we will use this deployment for autoscaling, and also we will expose this to internet using AWS Loadbalancer controller. Let's declare a staging namespace. Then the deployment object. It is a simple PHP Apache image that is provided by Kubernetes community to test autoscaling. The important part here is the resource block. AWS Fargate will create a dedicated node for your application, so your resource limit and request should match. Alright, let's go and create a deployment. In the first window, run get pods. And in the second one, use kubectl to apply deployment. Based on my experience, it takes about a minute for AWS Fargate to create a node. If it will take more than that, try to describe the pod to get an error or get the events from that namespace. Usually, it's enough for troubleshooting. To be able to autoscale our app in Kubernetes, we can use either Prometheus or a metrics server as a source for CPU and memory usage. Since we're using Terraform to provision our infrastructure, let's use Terraform Helm provider to deploy the metric server as well. There are multiple ways to authenticate with Kubernetes. If you use EKS, the preferred method would be to get a temporary token to authenticate with Kubernetes API server and deploy a Helm chart. This AWS command is part of the provider, so you don't need to install anything extra. Next is the Helm release. Give it a name metrics server, specify the namespace, version, and I disabled internal metrics, which is actually a default setting. We also need to explicitly depend on the kubesystem AWS Fargate profile. Since we use a new Helm provider, we need to initialize Terraform again and apply after. If it fails to deploy the Helm chart, you can check the status of the Helm release. Also, check the status of the pod. In case the pod was not able to be scheduled, it may fail the Terraform. Before we can test autoscaling, we need to create a service for our deployment. Make sure that you specify the same namespace where you deployed the Apache. Then, fairly simple autoscaling policy. Specify the minimum number of pods and the maximum. Then the reference to the deployment object. For the target, let's just use the CPU threshold. If the average CPU usage of all pods in this deployment exceeds 50%, the horizontal pod autoscaler will add additional replica. Now, you need to remove the replica count from the deployment itself, in case you store your config in the Git and synchronize with Kubernetes. This time we can apply the whole folder. For the demo, again, split the screen. In the first window, we can run get pods. Right now, we have a single replica. In the second, you can watch horizontal pod autoscaler. It takes a few seconds for autoscaler to correctly update targets. Lastly, let's run the load generating tool. It will spin up additional pod and continuously run CPU-intensive tasks on Apache. Now you can see that the CPU usage goes up. When it reaches 50%, we will get a new replica. If it's not enough to bring CPU usage under 50%, autoscaler will create another one. When you use AWS Fargate, you don't need to worry about cluster autoscaler, since AWS Fargate automatically scales based on the pod requests. Alright, now we have a maximum number of pods ready to get the load. Amazon EKS must periodically patch AWS Fargate pods to keep them secure. Sometimes it means that pods needs to be recreated. To limit impact on your application, you should set appropriate pod disruption budgets, PDBs, to control the number of pods that are down at the same time. In this example, we limit to one unavailable pod at any given time. You also need to match the label on the deployment object to select appropriate pods. In this case, we use label run equal to PHP Apache. Let's apply it and get PDBs in the staging namespace. You can see in real time how many pods can be unavailable for this deployment. You can associate IAM role with Kubernetes service account. This service account can then provide AWS permissions to the containers in any pod that uses that service account. With this feature, you no longer need to provide extended permissions to all Kubernetes nodes, so that pods on those nodes can call AWS APIs. Run Terraform init and apply. You can use list OpenID connect providers command to find out if the provider was created. The next step is to deploy AWS Loadbalancer controller, but first we need to create IAM role and establish trust with Kubernetes service account. We're going to deploy controller to the kube system namespace. Let's call Kubernetes service account AWS Loadbalancer controller. Then we need to grant AWS permissions to that role to allow create and manage load balancers on our behalf. AWS Load Balancer controller will create application load balancer for each ingress and network load balancer for typical service of type load balancer. I have a dedicated video with examples. Let's attach this policy to IAM role. For the convenience, we can print out the IRN of the IAM role to the console. We would need to use it to annotate Kubernetes service account. Also, let's create AWS Load Balancer controller IAM policy. You can get it from the official project for the controller. Finally, we need to deploy controller to Kubernetes using Helm. It's going to be deployed to the same kubesystem namespace. If you decide to deploy to a different namespace, you also need to create AWS Fargate profile for that namespace. There are a few variables that we need to override in that Helm chart. First is the cluster name, then the image tag. For production, you may want to deploy more than one replica. Then the service account name in Kubernetes and the annotation with IRN of that IAM role. We can pull it dynamically from the Terraform resource. AWS Fargate does not have access to the EC2 metadata server, so you need to explicitly specify the region and VPC ID. Now we can apply Terraform. You can check the Helm status, also the pod status. In the following example, we will be using this Ingress class created by AWS Loadbalancer controller. Next, let's create Ingress to expose Apache to the internet using AWS Loadbalancer controller. First, it's going to be a plain HTTP, and in the following example, we will attach a certificate to this load balancer to terminate TLS. By default, AWS Load Balancer controller will create load balancers with private IPs only. They can only be accessed within your VPC. To change that, we can use annotations. In general, AWS Load Balancer controller supports two modes: instance mode and IP mode. AWS Fargate can only be used with IP mode. It will create a target group in AWS and use the pod IP address to route traffic. The rest is pretty standard. Specify the host and the path. I highly recommend when you create your first ingress, check the logs on the controller to make sure that there are no errors. When you apply the ingress, the controller will reconcile and create application load balancer. If you see permission denied or similar error, check if the IAM role is properly configured to work with Kubernetes service account. To verify the ingress, we need to create CNAME record in your DNS hosting provider and point to the load balancer hostname. Check if you can correctly resolve DNS. Then you can use curl or go to the browser to access the Apache server. It's very unlikely that you would want to expose your service using plain HTTP protocol. Let's secure our Apache server with TLS. First, we need to request a certificate from the AWS Certificate Manager. The fully qualified domain name should match the host on your Ingress object. To prove ownership of the domain, select DNS validation. AWS will ask you to create a CNAME record to prove that you control DNS. If you use Route 53, you should see a button to automatically create that record. If you host your domain outside of AWS, you would need to create it manually. In a few minutes, your certificate status should transition to issued. Then we can use either the auto-discovery mechanism or explicitly specify the IRN of the certificate. You can copy it from the AWS console. The next annotation will configure listeners on the application load balancer. It will expose port 80 and 443. It's very common not to just refuse connection on port 80, but to redirect to a secure port. Now we can apply the ingress. To verify, you can find the load balancer in AWS and check the listeners. We have 2 ports and a default security policy. You can configure it with annotation as well. We also have a default rule on port 80 to redirect to 443. You can check the certificate status in the browser. You can see that the certificate is valid. AWS Load Balancer controller can also manage Kubernetes service of type load balancer. In tree, Kubernetes controller creates a classic load balancer, but the AWS Load Balancer controller will create a network load balancer. For that, you need to annotate your service with AWS Load Balancer type equal to external. Then it should also use IP mode instead of instance mode. There are a lot of annotations that give you ability to customize your network load balancer. When you apply a service, it should create a network load balancer and provide external IP address. To access it, you can use hostname of the load balancer directly. Currently, AWS Fargate doesn't support persistent volume backed by EBS. Right now, you can use only EFS. With EFS, you can use read-write-many mode and mount the same volume to multiple pods. With EBS, you can mount a volume only to a single pod. Let's create EFS file system using Terraform. You can tweak settings based on your requirements. I'll keep them default except for encryption. Now, AWS Fargate does not support dynamic provisioning, but regular EKS does. For Fargate, we need to create network endpoints, preferably for each availability zone. Also important to include the security group of the EKS cluster. Otherwise, you won't be able to allocate the volume. Let's apply Terraform. You can find EFS in AWS console. We have 2 network endpoints and security groups. Now let's create a storage class for EFS. Then the persistent volume. EFS automatically grows and shrinks, but persistent volume requires us to provide some sort of capacity. It can be anything. Also, you need to specify your EFS ID under volume handle. You can get it from AWS. Next is the persistent volume claim. Make sure that you use the same storage class. Also, we can use read-write many here. Finally, let's create a pod and mount that volume to the data directory. In the terminal, for the first time, you can watch staging events in case you get error. When you apply, first it will take a minute or so for AWS Fargate to spin up the node, and then it will allocate volume from the EFS file system. If you misconfigured something, the pod would be stuck in container creating state. In our case, pod was successfully created and running now. You can also get persistent volume claims. Status should be bound. AWS Fargate can be helpful in keeping costs under control. From my experience, it's hard to maintain the maximum utilization of Kubernetes resources, especially if you have a bunch of node groups in your cluster. In the next video, we will go over another solution for Kubernetes node autoscaling. It's called Carpenter.